Check it out now, y'all.
nanoHUB-U, online instruction.
Hello and welcome back to our last lecture of week 4 in nanoHUB-U's Introduction to Bioelectricity. This week we have been talking about the Hodgkin-Huxley Model. We talked about the history of Hodgkin and Huxley, we talked about the equivalent circuit they developed, the equation, we derived the equation which describes that circuit, and then we began to make predictions based on that equation. And if you recall from the last 2 lectures, I said, and I'll say this again, because it really bears remembering that the value of a model is exclusively determined by whether or not that model allows you to make predictions about things that you don't already know. A model that tells you what you already knew is just an exercise in programming. So the beauty of Hodgkin and Huxley is that it makes predictions about things that were not known at the time, although today we know them to be true. So from the numerical solution to the Hodgkin-Huxley model and equation, we can make predictions. We made 4 in the last lecture. We'll make 4 more predictions in this lecture. The 5th prediction is anode-break excitation. So if you recall, we left off with this idea that neurons are tuned to respond preferentially to change, rather than responding to a constant stimulus. So over time, if you apply a constant stimulus, you get accommodation. And accommodation means that the amount of firing that you're going to get for that same stimulus is going to go down and down and down as time progresses. And so what we look at here is not constant stimulus, or not rather a constant excitatory stimulus, but what happens if you apply a constant inhibitory stimulus. So if you apply a constant hyperpolarizing current, postsynaptic current, then the membrane voltage is going to drop. It's going to be the integral of that current over time is going to be how much the membrane current drops by, right? So the membrane current begins to drop, and then if you stop the hyperpolarizing or the inhibitory stimulus, and you return back to a current of 0, the membrane voltage will begin to recover, and then something very interesting will happen. It'll fire a train of action potentials. And it'll fire a train of action potentials without the membrane voltage ever having crossed the original threshold. In fact, you're not applying a stimulating current at all. So what is happening? What is happening in this window that causes the membrane voltage to drop, and then when we relax or we release the membrane voltage to snap back up, but then to fire action potentials? Why do these action potentials happen? And the answer is similar to what we had in accommodation. But whereas in accommodation, the threshold voltage began to rise with constant stimulation, excitatory stimulation, in anode-break excitation, the threshold voltage, which we map here as a function of time, begins to drop. From minus 40 where it starts, it begins to drop over time with its inhibitory current. And what happens is that when you stop that current and you allow the membrane voltage to return back to minus 65 millivolts, the threshold voltage is now below minus 65 millivolts. And so the resting membrane potential is now sufficient to fire an action potential. And in fact, it'll continue to fire action potentials as the threshold voltage begins to rise back up again, and it'll only stop firing action potentials when the threshold voltage returns to normal, or returns above the resting membrane potential. So you have a situation where you can excite a neuron, essentially, by inhibiting it, right? You can apply an inhibitory stimulus to a neuron over a long period of time, and then when you stop inhibiting it, it'll react to the change. And without ever having received a stimulus, it'll react to the change in such a way that it'll begin firing again. And in fact, this type of circuitry is essential in what are called rhythm generators in the brain. So those are circuits in which you can have 2 neurons, 2 inhibitory neurons talking to each other, where one inhibitory neuron fires at an initial rate. And because it fires, it creates this negative postsynaptic current in the postsynaptic neuron. The postsynaptic current hyperpolarizes that neuron, but it also drops its resting potential. Eventually, the first neuron will stop firing, and then the second neuron will begin to fire. Now when the second neuron begins to fire, it inhibits the first neuron, hyperpolarizing it and lowering its threshold voltage. At some point, the second neuron will stop firing because its own threshold voltage will have returned above the resting potential. When it stops firing, the first neuron snaps back and it begins to fire because its threshold voltage is now lower than the resting potential. And on and on and on. So if you can get past the initial difficulty of why does that first neuron fire the first time, then you can see how these two neurons will fire alternating one from the other. And that's how you make the clock out of two neurons inside of the brain using anode-break excitation. So it's a fascinating result. It's something you can observe in tissue culture, cell culture, brain slices, live animals, everywhere in the brain, and it was predicted by the Hodgkin-Huxley equation, and it works beautifully. The next prediction relates to frequency coding. So in frequency coding, we talked at the very beginning of the semester that action potentials are not graded. So if you have a postsynaptic potential, say an excitatory and inhibitory postsynaptic potential, if you have more neurotransmitter released into the synaptic cleft, you're going to get a greater postsynaptic potential. You're either going to get a larger excitatory postsynaptic potential or a more negative inhibitory postsynaptic potential, right? So they're amplitude modulated. The amount of excitation or inhibition is proportional to the amplitude of the voltage that you're going to see in that postsynaptic potential. Action potentials are not like that. Action potentials are all or nothing. They go from a negative minus 65 millivolts, which is the resting potential for potassium, up to about 20 millivolts, which is the resting potential for sodium, and then back down. They go from minus 65 to 20, minus 65 to 20 all day long. You don't get big action potentials, little action potentials. You don't get long action potentials and short action potentials. An action potential within a certain window of variability is an all or nothing event. It's much like the binary ones and zeros that you would expect to see in your computer. So then the question becomes, well, if it's a 1 or a 0, then I know how to distinguish between an event as a 1 and a non-event as a 0. But how do I tell the difference between a big event and a small event? So if I have a neuron that's tied to a rod in the eye that's going to detect light or the absence of light, well, I can see light versus absence of light, but how do I tell the difference between a cloudy day and a sunny day? How do I tell the difference between the light being bright and the light being dim? You know, one way is to have more neurons firing, but another way is to encode that information in the way that the neuron fires, and that's done with frequency coding. So if you have a postsynaptic current, again, that we apply to the neuron, and we're depolarizing the neuron for a length of time, you're going to get a certain firing rate in that neuron. And if you wait a long period of time, because of accommodation, that firing rate is going to decrease. And if it's an inhibitory current, and you wait a long period of time and then you stop, the firing is going to spontaneously occur because of anode-break excitation. But here what we're seeing is we have a stimulus over a short period of time. And in this short period of time, we're going to see a certain number of action potentials. If we then increase the stimulus level, so it's the same period of time, but the stimulus level goes up, we're going to see, as we move from the solid line to the dashed line, additional action potentials at these dashed lines. Now, these additional action potentials will be limited only by the absolute refractory period. So the absolute refractory period will tell you what the minimum amount of time that your neuron needs to rest before it can fire again is. The relative refractory period will tell you what is the amount of time that it would like to rest. So the amount of time that you need to wait before the neuron can fire again with the same stimulus as it had originally. But the absolute refractory period will tell you what the maximum firing rate or frequency of that neuron is. And then the number of action potentials you have within a fixed window, the frequency, the cycles per second or hertz of this firing, is going to be determined by the amplitude of the postsynaptic current. So the excitation in a neuron, there is a gradient from more to less, but it's not more amplitude to less amplitude, it's higher frequency to lower frequency. So it's frequency coded. And when you take the Hodgkin-Huxley equation and you numerically solve it and you apply a stimulus, you get a certain number of action potentials. And if you increase the stimulus, you get a higher frequency of action potentials. And from that, they were able to predict that in the brain, the way that information was coded for amplitude was by using frequency. And then go into the laboratory and test and find that, in fact, that's exactly how it works. So neurons encode intensity of stimulation with the frequency of their firing rate. And that was the sixth prediction from Hodgkin and Huxley. The seventh prediction is this one regarding subthreshold oscillations. So if you look at an action potential and you measure it on an oscilloscope, you'll see this characteristic shape where you start at the resting potential, you go up to about 20 millivolts, you come back down, you have a little bit of undershoot before you level off. But if you take that leveling off, or really if you take any part of this action potential and you zoom into it, right, you look very closely at this flat band, you find that it's actually not flat, but you have these little oscillations. All of these oscillations happen below the threshold voltage. That's why we call them subthreshold. So they never trigger an action potential by themselves, but you have these little oscillations. And it behaves like if you had an additional component in your Hodgkin-Huxley equivalent circuit model. So when we looked at the equivalent circuit, remember that this equivalent circuit was meant to fill in the gap just for one infinitesimal segment of the core conductor model. As you go through each infinitesimal segment, you're going to add these equivalent circuits, where now we've moved to local variables rather than total variables. So looking at local variables, you're going to have these equivalent circuits, and you're going to have something joining one segment to the next. And that something behaves like an inductor. You can say that this inductor represents the distance between along a wire, and a wire looks like an inductor. Any length of wire acts like an inductor. The longer the wire, the larger the inductor. But there's more to it than that here, in that what you're really getting is a resonant behavior that is partially perhaps a result of just the electrical resonance of that wire, but it's certainly a result of the relationship between ion channels in one segment and in the next segment. So each segment does not operate in isolation, but rather they operate in some sort of relation to one another. And so you get this oscillation as energy gets passed back and forth between adjacent segments along an axon. And you can observe that physically in an action potential as these subthreshold oscillations. So you would expect to see these, because if you map out the numerical solution for Hodgkin-Huxley and you zoom in, you see them. And then nobody had ever observed these in living subjects, but if you go in and you measure them precisely and really zoom in on those flat parts, you do see them in living subjects. And the role that these oscillations play, whether they're just a side effect of the structure of the neuron, or whether they have some role in communication, intracellular communication within the neuron, is an open question. But it's a very interesting question, and that's the result of our seventh prediction from Hodgkin and Huxley. The eighth and final prediction relates to temperature dependence. So one last time, we'll plot out the membrane voltage as a function of time. And we'll see our action potential begin at minus 65 millivolts. Then the sodium ion channels open, the potassium ion channels close. Sodium rushes into the cell, depolarizing it. The sodium ion channels close, potassium ion channels reopen. Potassium rushes out of the cell, hyperpolarizing it. You have a little undershoot, and you go back to your resting membrane potential. You break up this membrane voltage shift into ionic currents. We're shown here in brown or in orange. We can see the sodium current, and shown here in yellow, you can see the potassium current. And the dashed line where the sodium current into the cell and the potassium current out of the cell are equal to each other is when you have zero net current, and that's where you have the peak of your action potential. And after that, potassium takes over, sodium diminishes, and you restore the membrane potential. We call this first current, this first sodium current into the cell, we called it the transient inward current. Transient because it only lasts for a certain period of time. The second current, in yellow, the potassium current out of the cell, we called the delayed outward current. And when we first talked about these currents, I mentioned that there's this question about what causes that delay. And it turns out that that delay is temperature dependent. And this is something that Hodgkin and Huxley predicted. And so what they found is that as you increase the temperature, and remember that the Nernst potential is temperature dependent, and the membrane potential is a function of the Nernst potential, and the ionic gating forces in the Hodgkin-Huxley equation are themselves functions of the membrane potential, which is a function of the Nernst potential. So as you increase the temperature, the delay of the delayed outward current decreases. So this yellow curve shifts left. And what that means is that more of the potassium outward current and the sodium inward current overlap. And when they overlap, they cancel each other out to some extent. And the net result is that as you increase the temperature, the amplitude of your action potential decreases. Now this is very interesting, because if you think back to how the axon works, you have this long length of axon, and you can create an action potential and have it flow passively, but at some point it'll become so small that it won't be big enough to trigger an action potential at the end of the axon, which means that you won't get the opening of those voltage-gated calcium channels, which come rush in and that lead to the vesicles bonding with a neuronal membrane and releasing neurotransmitter, which leads to the excitatory or inhibitory postsynaptic potential. So if the action potential is not strong enough to regenerate at the terminal of the axon, you're not going to get neurotransmitter release and you're not going to get communication with the postsynaptic neuron, which means that your neuron is useless, right? If you can't communicate to the next neuron, then what are you there for? So it's essential that you have that, but it's also essential that that happen quickly. And in order to get that to happen quickly, we take advantage of the speed of passive conduction and the fact that the length over which you can maintain that amplitude increases when you myelinate by wrapping this neuron in this insulator, myelin, that allows us to flow passively from the axon hillock to the first node of Ranvier, regenerate, flow to the next node of Ranvier, regenerate, and so on down the line until we get to the end of the axon. But if you decrease the amplitude of the action potential, the attenuation as a function of distance is going to remain the same. What will happen is that your action potential, now when it reaches the next node, will no longer be big enough to regenerate. So this decrease in amplitude is something to worry about. And so this relationship with temperature is something to worry about. And in fact, it turns out that Hodgkin and Huxley, having seen this prediction from their model, realized that they had done all of their experiments in giant squid axons. And giant squid axon experiments happen at room temperature. You take a saline solution, you take a giant squid axon, and you drop it into your saline solution, which is at somewhere in the vicinity of 20 degrees Celsius or 72 degrees Fahrenheit. That's your room temperature. What happens in a mammalian neuron? You take that same solution and you raise the temperature from 20 degrees Celsius to 37 degrees Celsius, or from 72 degrees Fahrenheit to 98.6 degrees Fahrenheit. And what ends up happening is that these two currents, the transient inward current and the delayed outward current, overlap so much that the amplitude is decreased to such an extent that the action potential no longer reaches the end of the axon. And so the question then becomes, well then how does this work in mammalian neurons? Because the internode spacing, the length of those segments of myelin, is very similar to what you see in the giant squid axon. So why is it that the action potential works in mammals? And the answer is that in mammals and mammalian neurons, if you look at the density of potassium ion channels in the node of Ranvier, you find that they are very, very small. There is a much lower density of potassium ion channels in the node of Ranvier in a mammalian neuron than there is in a cold-blooded animal. And that's not just a prediction about the temperature dependence, but then it's a prediction about the anatomy and the density of ion channels that you would expect to see that was made on the basis of the Hodgkin-Huxley equation and that was borne out by experimental observation. And so that's where I'll leave you with Hodgkin-Huxley, and that's the eighth and final prediction. Next week, in week 5, we'll begin applying the things we've learned so far, all the way back from the basic anatomy we covered in week 1, through the Nernst equation, and then the core conductor equation, the cable equation, the Hodgkin-Huxley equation, putting that all together and begin to talk about how all of these components fit into our understanding of diseases like Parkinson's disease, epilepsy, phenomena like drug addiction, applications like targeted muscle reinnervation and prosthesis control, and a new technique called optogenetics. So we'll bring it all together. We'll talk about 5 specific applications of bioelectricity and the cutting edge in those applications as it stands today. I'll see you next week.